It says, you have a compound with the following percentage composition. So you have carbon with 65.45. 65.45. You have hydrogen with 5.492. And you have oxygen with 29.060. This is exactly like we did in class. Yes. I gave you the different percentages. I give you the molar mass of 110. So I tell you the molar mass is 110 grams per mole. And then there's a mistake in the question. For that, I do apologize. The question reads there, calculate the molar mass of the compound. It should be calculate the molecular formula. Sorry. I'm also human. I make mistakes. Okay, right. So, not the molecular mass, because that I did give you, 110. I was for the molecular formula. So, just change the question, please, in your notes. The molecular formula. All right. So, the first thing you need to do is you go calculate the mole. Now, to calculate the mole, you need to use that formula, and you get a mark for that formula. Okay, so you need to show it. You don't have to show it 3 times, only show it once. Then we are going to calculate the mole for each one. Mama, we're going to start with you there at the back. So I hope your calculator is out if you didn't do it. Okay, Mama, what did you get for the first one? Okay, and did you do it? Aito. Yes, what did you? Oh, 5.492 because it's the same one. The last one? Okay, so remember there you do not round off just yet. Okay, and then you want your ratio. And for your ratio, you're going to divide by the smallest one. Okay, so the smallest one is the one at the bottom. So that is obviously 1. What is the rest, Kumo? Yes? Yes. You round up or down for the ratio, except if you get something, let's say you get 2.45, then it's very close to 2.5. Then you leave it at 2.5, but we haven't done an example like that just yet. But the rest you round up or you round down. Who is absent here? Declan. And the next one? Both of them 3. Because they're more or less the same. Okay, so you get this to be C3H3O. Okay, that there is called the empirical formula, the simplest ratio. But they ask for the molecular formula. So it can be a multiple of that. It doesn't have to be, but it can be. So what you do is you first go get the molar mass for that compound. Not 6, sorry. 3. Okay, so that is 3 times 12 plus 3 times 1 plus 16, and I think that gives you 55. Okay, then so that is the mass for the empirical formula. But we want the molecular formula, and they gave us the mass of the molecular formula. So what you do is you take the molecular formula divided by the empirical formula. So they gave that to you to be 110, the mass, in the question, divided by 55, and that gives you 2. So that means the molecular formula is twice the empirical formula. Ooh, are you all right, Siamo? Okay. So you're going to take this thing and you're going to multiply it by 2. So the molecular formula is the C6H6O2. Okay, and something you don't need to know, but for those that are interested, this is called hexanoic acid. What does hex mean? 6. So 6 carbons, hexanoic acid. But it's not something you need to know now. Next year, yes. Oh, you guys are going to complain next year a lot. Because there's a lot of study work. If I'm still alive next year, I will be teaching you. Maybe I'm going to go to heaven. It's better than earth. Yes. I will not be sad if I die. Yes. Say again. Up. Alright. The next one. Okay, now the next one is a bit more difficult. It says there, you have a 25-gram sample of a compound that has a molar mass of 142. Does yours say 142? That was a mistake, I should have changed. Good. 142 grams per mole. And it is looked at, and then they say they found the following. Can I go down, Bookie? Okay. They found that sodium's mass is 8,0925. Sulfur is 5.6425. And oxygen is 11.265. Okay, so now, and I did mention this quickly in class, now they didn't give you the percentages, they gave you the mass out of 25 grams. You don't have to take it to percentages again. You can, but it's extra work. You can just leave this in the mass form that it is. Because if you calculate the mole, it's mass over molar mass. And this is already the mass, the grams. So you don't have to take it to percentages. You can just leave it as it is given to you. This question comes from a past paper. Okay, so they might ask it like this. Right, we need to go calculate the mole. So that is 8,0925 divided by 23. And then we have 5.6425 divided by 32. And 11.265 divided by 16. Princess. So it's just like a 3. Okay, it's enough. Okay, Jabu, next one. Ooh, louder. 175. Never. Sorry, go again. 1, 7. 5. 7, 8. That's enough. That's good. So one of the last one. + 7040. All right. Then you need to get the ratio. For the ratio, you need to divide by the smallest one, which will give you 1. Underneath the first one, there at the top, if you divide that by the smallest one, you're going to do the last one. What? Then man, just read out loud. Which one?
This right here.
It's not the end of the world. It's really not the end of the world. What do you get underneath? So 2. Bookie, the last one? So if you round off, 4. Okay, so you get that to be Na2SO4. Now that should look familiar. That's a compound that you should have seen in your science life before. Tell me, what is the name of that compound?
Sodium.
No. Tiamo? Yes, sodium sulfate. All right. Now we determined that is the empirical formula. Let's check the molecular formula. We must get the mass. It's 23 times 2 plus 32 plus 4 times 16. And if you calculate that, you get it to be 142. So what we've proven there is that the mass of the empirical formula is the same as the mass for the molecular formula. They are both 142. So that means the molecular formula is just Na2SO4. Yes, Tawana? You just have to... Did you stop there?
Yes. I actually divided. I did it the way you do it.
And then you showed it's 1/1. And then you must just say the molecular formula is there for that. Sharp. Okay. Okay, can we go back to your notes? It's in that box. Yes. Oh, I have to go copy more. I don't have any small ones left. All right. So we are busy here with the limiting reagent. Yes. He just asked. I have to go copy. I handed out all of them out. Right. So we are busy with the limiting reagent. And we looked at a reaction and we said, okay, if we have, or if the mole ratio is 4:5, so that is on page 10. If the mole ratio is 4:5, but we only have 1 and 2, then we determined which one is a limiting reagent. Which one do we have not enough of? And we discussed that is to be ammonia. And then we say we use all of the ammonia, and ammonia will determine how much products we will use. We will get. Okay, so we did all of that, and now they ask at the last question, what is the total volume of gas? Do they say which gas? No. So it's all the gases, the total volume of gas present when the reaction is complete. Okay, now why do they say that? Because they are all gases. Okay, and this all happens in one container. So it's not as if you can see, oh, but there goes a purple gas and a pink gas. And you just see a white smoke of all of them. Okay, so we can't say how much of that is left over at the end. We are going to say, okay, how much of the gases, all the gases are left over. Now, we've already, in our mole table, we have already determined we have so much mole left of this. We gain so much, we gain so much. So I can get the total mole of gas at the end. Okay, so I can write here, the mole of gas will be 0.75 plus 1 plus 1.5. So I got it, oopsie, these values from the table. So these values I got from there. Okay, so that gives me a total mole of 3.25. Okay, but the question was not what is the mole left over. They asked for the volume. So we're going to use this formula of volume at STP. Where am I with my questions? Morsi. What does STP stand for? And? Pressure. And what is standard temperature? No, standard temperature is 0 degrees Celsius. Okay, and Boitsepu.
72.8.
And the unit?
Decimeter per cubic.
Not per cubic, just cube, but good. Bongani, decimeters cubed is the same as what? No. It's the same as liters. And remember, centimeters cubed is the same as milliliters. All right. Going. Gone. Okay. Now, when I started this mole table thing, I said something, I don't know if you remember it. I said I am going to work mostly with the mole ratio. Okay, I'm going to convert everything into moles and go to a mole table. Okay, but I did say if you do it at another school, extra class or whatever, they can use the mass ratio and they can use the volume ratio. Now I'm just going to do one example with the volume ratio, just to show you that it is possible. But you're only allowed to compare the volumes with one another if you're working with gases. Okay, so you can't compare the volume of a solid with a gas. So if they are all gases, then you can use the volume ratio. And if you are at the same temperature and pressure, so either STP or any same temperature and pressure. So they must all have the same environment. Okay, so that's the one that we're going to do now. They say there, you have 44.8 liters of nitrogen gas and 140 liters of hydrogen gas that react at STP. So as you can see, sorry, I should have said the gas. They're all gases, check, and they're all at the same temperature and pressure. STP here, but it doesn't have to be at STP. It can be at the same temperature and pressure. Now we can compare the volumes with one another. Now they ask determine the limiting reagent, calculate the volume of gas formed, and then calculate the total volume. You are, same with the mole table, you are first going to start with your balanced equation. Always. Okay, that is 1 to 3 to 2, and I'm just going to highlight this to remember this is just my recipe. This is not what I have. Okay, so I'm just going to say again, normally I convert everything to moles, but now because they are all gases and at the same temperature and pressure, I can compare the volumes. So now I'm going to write here beginning, change, end, but I'm going to fill in the volumes. Okay, this volume at the beginning was 44.8 liters and this was 140 liters. How much of the product do you have at the beginning? 0. Always 0. Right. Now I can't say that I'm going to use all of this and I'm going to use all of that to get 0 and 0. Okay, I have to find the limiting reagent. You remember the sandwiches and the cheese yesterday? Okay. So I'm going to do this just on my right hand side. You can do it at the bottom. I think you'll have enough space for everything. We are going to determine question E, the limiting reagent. Okay, so I'm going to write ammonia versus hydrogen is 1 to 3. Yes? 16p. STP is atmospheric pressure. So the temperature is 0 degrees Celsius and the pressure is 101.3 kilopascal. Okay, now in your head you say, all right, the ratio is 1 to 3. What's doing that? You hear it?
It's a sign you should stop working, man.
Okay. All right. The ratio is 1 to 3. In your head, you say, if I use, is it outside? If I use all of that, how much of this will I need? So if I use 44.8, how much will I need? Okay, so you're going to say times 3. What you do on the one side, you must do on the other side. Liakwe, what do you get? 0.4. Okay, so that is how much you need. How much do I have? I have 140. So I have 140 liters. So do I have enough? Yes, you have more than enough. So yes, you have enough. Mean that one is in excess, and the other one is my limiting reagent. Okay, I'm just gonna, so this is sufficient in a test and exam to show this is enough. I'm just going to show you the other way around as well. So you can also have gone hydrogen versus ammonia. Not ammonia, nitrogen. It's 3 to 1. So I'm just swapping them around. And then you say, okay, if I use all of that, how much of that will I need? So if I use 140, how much of that will I need? So there you divide by 3. Mama, what do you get? Seven. Okay, so you say, right, I need 46.67. How much do I have? 44.8. Do I have enough? No, I do not have enough. So I only have 44.8, meaning I don't have enough. So proven again, that is the limiting reagent, and that is in excess. Okay, so we've proven the same thing twice. We've proven that nitrogen gas is the limiting reagent. Okay, and the one that is the limiting reagent, you know two things of. Number one, you use all of it so that you have 0 left at the end. And number two, the limiting reagent will determine how much products you will get. Okay. Now, how much will we delete here? We are going to delete or use 134. Okay, we said because if we use 44, we're going to use so much of that. So if we use 44, we're going to use minus 134.4. Okay, and the mole ratio here is 1 to 2. So how much will you get there? You're going to multiply that by 2. How much is that? 90.6. 98. No, 90. 89.6. Okay, so here you have 89.6 left, and I think there you have 5.6. Okay, so what did we just do? How is this different? Now, instead of converting all of this into moles, we used volumes. Why? Because we're busy with gases and they're at the same temperature and pressure. If it's not gases and not the same temperature and pressure, then you have to convert everything to moles. Okay, right. So this was question E. Sorry, question E was determine the limiting reagent, and we determined it to be nitrogen. Then they asked calculate the volume of ammonia gas that formed. We got it to be 89.6. So you can either, if you did it in your table, you can either just say refer to table and then say ammonia is 89.6 decimeters cubed, or you can do the mole ratio thing. Okay, so or you could have said nitrogen versus ammonia is 1 to 2. Okay, but how much nitrogen did we use? 44.8. So then you say from there to there, you multiply by 2. So here you get 89.6 decimeters cubed. Alright, and then question G. With question G, they ask, calculate the total volume of gas, they don't say which gas, so all the gases, present when the reaction is complete. So when the reaction was complete, that was our volume of gas left over. So I'm just going to add those two together. So we're going to say the volume of gas will be 5.6 plus 89.6, and that gives you 95.2, I think, decimeters cubed. Right, so on to the next idea. Okay? You can, I'm going to do the table in front. Okay, so the next idea has to do with percentage yield. Now can anyone tell me what is yield? Yield. Say again? Yield. Yield.
Isn't like I was sick and I healed?
No, not like yield.
Yield.
Okay. Look at the spelling there. Yield. You have to elaborate more on that? No. I say yield. Okay, but it can be. I'm going to use it as a piece of answer. If do you have vegetable gardens at home? No. You should start.
Yes.
A vegetable garden, like grow your own beans. It's so easy.
I mean,
and you get lots. Alright. Okay, so when they say you grow stuff at home, then you think, oh, what was your yield this year? Like, how much did you get? How much beans did you get, or tomatoes did you get, or whatever? Okay, now in science, the yield is how much products you get. Let's say, have you ever made, I think I've used this example last year to start this chapter with. Have you ever made cupcakes or something with that little packets, that small packets that you buy at the shop? Easy. Then the easy mix says, makes 24 cupcakes. Okay? Now you go home, you mix, and you bake it, and you get how much? 20. It depends how much of the pancake you ate while you made it. It depends how much came up as a flop. It depends how big the size of your pans are. So it depends on a lot of human error. The same thing in science. We say, alright, we have a balanced equation. So we should get, if we add 1 of this and 2 of this, we should get 5 of this. And now we do it and we don't get 5. Okay? So, and that's very normal in science. So we will determine the percentage yield. What is the percentage of the things that I actually got? It's like when you do a test, the test is out of 100. What is the percentage that you got? Insert your value here out of 100. Okay, right now. Okay, so I'm just going to show you a type of example that we are going to do, or the wording there. Here we have marble. Marble we use for kitchen countertops. But we also use marble in the powder form, we use it on the rugby field to make the lines and the stuff like that. Okay, so this is marble, calcium carbonate. Oh, I actually wanted another one. Okay, calcium carbonate. And this here is calcium hydroxide. This is called slate lime. Can you see they look the same? Not the same white. So if we make this one fine, it will also give you this color or this powder, more or less. Okay, I'm going to send this around just so you see. This is just a rock. Okay, it's not something in your hands. You can taste it if you want. It's so nice. I'm just going to send it around. This was just powder. I don't want to mix. I just forgot to bring the other one. So this is calcium carbonate, just a powder. So that's what it is in powder form. Alright, now when you add these two things together, I'm just going to write here for you. So when you add, you have calcium carbonate, the solid, the powder. You add hydrochloric acid to it. Guys, then that gives you calcium chloride. Now that is a solid, normally it's a salt, but it's going to dissolve, so it will be aqueous now. Okay, and I'll show you now. Then you're also going to get water, the liquid, and then you're going to see a gas form. It's carbon dioxide gas will form. Okay, now this will all happen in one container. So it's not like we have two separate containers. We have one container, that last beaker, in which this will take place. Okay. What you will see happening is you will see it looks like it's burning or boiling. It will make a gas. So there's a carbon dioxide gas that forms. Then you will also see there's a liquid, the water. And then you will see it turns yellow. Now it shouldn't actually turn yellow. It turns yellow because I made this with Paris tap water. But it's all my Paris tap water. So it shouldn't turn yellow. It should actually be just a whitish liquid. Okay, it's not the end of the world. Alright, so I'm going to show you. Alright, so you saw the gas that came off. The gas is carbon dioxide gas. You see the yellowish liquid. So it should be whitish actually. So we should see the salt floating around in the water, but the salt dissolves in the water, like normal salt dissolves in water. So that's why you only see the yellow substance. You don't see salt and water. All right. Then last thing, how do we taste for carbon dioxide? How do you taste if this gas is carbon dioxide? No. You let this in. You didn't last time.
Water and lime water.
Yes. You take water. If there's powder and you dissolve it in water, it becomes lime water. And if you bubble carbon dioxide gas through it, it becomes milky. Did you do it in class? Alright. Okay. So that is something that you should know. How do you taste for